Hi everyone, my name is Simran Khanuja and I'm a PhD student at Carnegie Mellon University. Today I'm very excited to be talking about our work on data efficient multilingual learning, which was done with amazing collaborators Srinivas, Lucio, and Graham. So let me motivate the problem with a hypothetical story, which is nonetheless reflective of real-world applications. So let's imagine this company, which is a healthcare company, and they have deployed this virtual healthcare assistant in India, which caters to multiple diverse Indian languages. Under the hood, what probably might be happening is that there is a language identification system which identifies which languages the user queries are from, and they would possibly be routed to smaller models which deal with a certain subset of these languages, and then finally the responses are sent back to the user. Now let's assume that they want to expand their services to neighboring countries like Nepal, Bhutan, Bangladesh, and they start receiving queries in languages which are unknown to them. The main question now is, how do they build their models or improve their models to deal with these queries which are in unknown languages? So a very practical first step for anyone would possibly be to identify which languages these queries are coming from. But they fail at this step alone because commercial language identification systems can't identify 98% of the world's languages. So what do they do next? They basically try to ask people and realize that, okay, these queries are coming from Tsonga and Tharu. The next step would be to try to get annotators to sort of label QA data in these languages, which they can use to either fine-tune or pre-train models downstream. But then they realize that crowdsourcing platforms lack support for these languages. So what can they do next? Well, they try to identify languages where annotators are available, and the main goal here is to be able to identify some higher resourced languages which are close enough to these target languages such that they can, transfer to these target languages. However, these tools also require linguistic feature information or past model performances to be able to identify the best transfer languages, and they aren't able to do this either. Finally, let's assume that by human intervention again, they are able to identify some higher resource languages like Nepali and Tibetan to transfer from. The last step would be to identify the right data to give to annotators such that it would best benefit their healthcare domain, right? Like we'll have data from News Corpora, from Wikipedia, multiple websites. So how do you identify the exact data points to label from these high resource languages? All of this kind of builds up to the main research question that we're trying to address here. And that is basically, how can we select the exact data points to give to annotators when we want a pre-trained multilingual model to perform well for a certain set of target languages in a certain domain? If we have access to like a huge data pool from multiple languages which is unlabeled, so how can we select those exact data points to label under our budget, right? And this is a very it's a very common problem in the real world. The framework that we build, DeMuX, to solve this problem can work without the need to identify languages, either in the source data or in the target data. We don't rely on linguistic feature information, so it is very inclusive in terms of all the languages or data that it can support. We don't lean on past model performances, and our methods also work when the source data that we have is completely disjoint from the target in terms of both domains and languages. So a very brief overview or a very high-level overview of how we do this is basically let's assume we have this unlabeled source data from a lot of languages. And we have certain small number of target data. So for us, this would be the user queries that we are receiving in Tsonga and Tharu. And this source data would represent all of the unlabeled data that we collect in Nepali and Tibetan. We would feed this data into the model of interest that we want to improve. And the DeMuX would basically select points from the source data which would best benefit your target given your pre-trained model, which we can then use to fine-tune our model, and we can continue this in an iterative fashion until we've reached our budget. So what are some other benefits of DeMuX? Basically, we get the exact data points to label from across multiple languages instead of just choosing a few best transfer languages. We also show that this is important because the data selected by DeMuX usually differs across tasks for the same target. So for example, we had Urdu as our target in one of the experiments, and DeMuX picks a lot of data points from Hindi for part-of-speech tagging, but from Farsi and Arabic for named entity recognition, because Farsi and Arabic share the same script with Urdu. So the data selected also provides some sort of insights into what factors the model leverages for better cross-lingual transfer. DeMuX can work with multiple target languages in your target data, and we also show that we can provide for huge boosts with very limited annotation budgets as well. So before I go into the methods, I just want to give a very brief background on multilingual fine-tuning. So typically what happens is that we pre-train a large model on unlabeled data from 100 plus languages, and to use it downstream, we gather small amounts of labeled data, which is typically in English because we have labeled data in English for most tasks. And then the model can perform well on all other languages seen during pre-training, even without access to labeled data. But there's a lot of active work on what kind of languages transfer best to a certain target. And there was this one influential work which talked about how even small amounts of in-language training data can give a huge boost in performance. So if our target is Urdu, just 10 to 15 samples of Urdu would help much, much more than 1,000 samples in English. The next thing I wanted to talk about is a brief background on active learning, because we use active learning strategies for our data selection. So active learning is a paradigm which helps inform annotation efforts. The premise is that you have a huge pool of unlabeled source data. So how can you identify, say you have 10,000 samples and you just have the budget to annotate 100 samples. How do you identify those 100 samples which would be most informative to your model, right? And the two major considerations for data selection, A is diversity. So you want the 100 samples to be representative of the 10,000 sample distribution. And B is uncertainty. So you'd want to select those samples which the model is most uncertain about, so that labeling them would help increase the robustness of your decision boundary. And hybrid approaches combine the two. So based off of these three factors, actually, we devised 3 active learning strategies for DeMuX. The first is called average dist. So here the light blue points are all of the source data that you have. The dark blue points are the points that are selected to be labeled, and pink points are your target data. So in average dist, it's very simple. We just select points which lie at a minimum average distance from all of the target points. Then there's a pure uncertainty-based method, which we call uncertainty, that chooses points that the model would potentially misclassify. So this is a 3-label classification, and if you think that the 3 labels lie at the 3 vertices, the strategy selects points which lie at decision boundaries, which would be highly uncertain for the model. And in KNN uncertainty, we try to combine the best of both, where we basically take top K neighbors of each of the target points, and then we prune that list to get the most uncertain samples based on our budget. So we asked 3 questions when we were designing these experiments. Can these 3 strategies benefit tasks with varying complexity? Does DeMuX work well across a varied set of target languages? And can we improve performance of multiple languages together at the same time? And the third question is, do these strategies work well across different multilingual models? And this is a very brief overview of our setup, which is pretty extensive in my opinion. So we have 3 setups where we take just a single target language, and 2 where we have multiple target languages that we are trying to improve performance of in one fine-tuning step. So the overall takeaways for us was that these strategies are able to perform better than baselines, which is like random selection or selecting an equal number of points from each of the source languages in 84% of the cases. And we are able to observe gains on multilingual target pools as well. Analyzing what kind of data is selected for the same language across tasks is also very interesting, like I mentioned earlier in the talk. We find that for certain easier tasks, maybe like token level tasks, the distance-based metrics matters more, but especially for question answering, it becomes more important to select uncertain points. So we observe this sort of different strategies working well across different task types, which is consistent with past work. And we also try this setting where we take very limited budgets, 10 to 50 samples, 100 samples, and we observe that we actually have much higher gains when the budget is very small, but the gains diminish as the budget increases, which is again typical of an active learning setup. And the last point that we wanted to emphasize is that it's not just the language distribution of the selected data points, but the actual points selected that really matters. Because when we replace the selected points with random samples, which nonetheless follow the selected language distribution, we see that performance declines. These are some results which I'm going to skip over for the interest of time. Just one bonus is that we extended this framework to support generation tasks, and we also tested on languages which are completely unseen in pre-training, which also yields positive results. So yeah, thank you so much for listening to our talk. Please feel free to reach out to me for a follow-up discussion. I'd be really happy to chat. This is the paper and this is the code. Yeah, thank you so much. Thank you for listening.